The next talk, still on deformation, is entitled On Bending in a as rigid as possible deformation energy. And the authors are Hugo Finnendahl and Marc Alexa, again from TU Berlin in Germany. And our speaker is Hugo.
Okay, yeah, hello everyone, yeah, thank you. And I will now present to you my findings that I discovered while writing up my PhD thesis. So one thing I learned over and over again while doing my PhD is writing things down helps you discover things. Usually I discover mistakes, but this time I discovered something new about the as rigid as possible energy, and Mark and I want to show it to you. Yes, so we are in the setting of mesh deformation, and we start with the original as rigid as possible paper that was presented 19 years ago here at SGP. And the idea is that we have this mesh and some constraints, and we can, or not, move around. Maybe I should have checked this. Yeah, and we see that the mesh deforms as rigid as possible. So we have as input vertices and triangles and some constraints colored in red, and we search for the optimal positions V using the same triangulations while fulfilling the constraints. And this is done using energy minimization. So we find the optimal V by minimizing the energy under the given constraints. And because we will take a deeper look into the energy, I will now go through the exact energy step by step and give you an intuition what it measures. First, let's ignore the weighting for now and take a look over which things we sum. Yeah, first, we sum over all vertices. So let's zoom into that and take a closer look. Given a vertex I, we sum over all neighboring vertices, colored in blue, and compute the edge vectors to each neighbor. And as they are both just vectors, we can visualize them on top of each other. So, yeah, they share the same coordinate system. Now we measure the squared distance, which is the distance of the corresponding blue endpoints of the edges. But before we measure the distance, we need to apply R, or Ri, to the input edges. So Ri is the rotation matrix, but not an arbitrary rotation matrix, but the rotation that minimizes the squared distance in the sum over the vertex V. So it rotates the input edges to minimize the distances. So the energy introduces auxiliary variables that get minimized on the fly. And for the intuition why this is as rigid as possible, remember that a rigid transformation allows only for translations and rotations. And translations are not penalized as we operate on edge vectors, and rotations are not penalized as Ri compensates for it. So the penalty measures the non-rigid transformations that are left over. So the question is now how to optimize this. And of course, we can do gradient descent, but Olga and Mark came up with a better optimization strategy enabling interactive deformations. And to get the idea, we rewrite this energy by first removing all the colors and simplify it by replacing the edges. So next, as we want to minimize this energy, we can move the inner minimization of the rotations into the outer minimization. So instead of only minimizing the vertex positions, we simultaneously minimize for the rotations as well, making the auxiliary variables an explicit parameter R. Okay, so now we have two sets of variables that we want to optimize, and unfortunately, the energy is not simple to optimize in V and R directly. But we can isolate them, which means we can do a block coordinate descent. Because given fixed vertices V, finding the optimal rotation per vertex is quite simple. First, compute the so-called cross-covariance matrix, then extract the optimal rotation using the polar decomposition. So now we have the optimal rotations per vertex, and to find the optimal vertex positions given these rotations, we just need to take a look at the energy and see that when R is fixed, everything is linear in the norm. And we can just use or solve this using a linear system of equations. And I added an image for the intuition on the right, which is not 100% correct, but more or less the vertices try to fit into the rotated versions of itself given the rotations of the neighbors. Okay, and because the rotations can be found locally, and the rotations can be found global. The rotations can be found locally, and the vertex positions can be found using a global linear system of equations. This is a local global optimization scheme, which we repeat until we converge. Okay. One last thing, you might notice that the linear system of equations for the global solve is called L. And this is no coincidence because Mark and Olga found that the best weights for each edge are the cotangent weights, leading to the fact that the system matrix is the discrete Laplace-Beltrami operator. Okay, this works and leads to impressive results given such a simple method, but sometimes it behaves weird. For example, here we have artifacts at the ear of the bunny without reason, and even sometimes we completely diverge. But luckily, 3 years later, there was a solution to this problem, because Chow and colleagues came up with a continuous energy that is very similar to ARAP. In the continuous setting, like we heard in the last presentation, we have a function f that maps between two surfaces. And Chow and colleagues defined an energy that integrates over the whole surface, and at each point x, it measures how much does the Jacobian of f at x differs from a perfect rotation. So they measure how well does the linear approximation of a deformation differ from a rotation, which does not only sound like ARAP, but also resembles the energy when discretizing it over a triangulation. Looking at it, we see that we have again two sums, a cotangent weighting, and again some norm of edge differences where one edge is rotated. But the devil is in the detail. If we compare the energies, we see that the summation is not over vertices, but triangles. So basically, we do everything per phase, hence the name phase ARAP. This makes the optimization process slightly different. First, the cross-covariance matrix is computed per triangle, and therefore the optimal rotations are also computed per triangle. And for the global step, we again end up with a Laplacian as system matrix, but the right-hand side differs a little bit, as we now have to incorporate the rotations per triangle instead of per vertex. So the energies and the optimization are very similar. And the reason why this is so similar is because the integrated Jacobian is the cross-covariance matrix when using the cotangent weights. So the cotangent weights that Mark and Olga used are in fact very important for this derivation, which is surprising, at least to me, because Mark told me that there's a completely different reason why they choose this weighting. And you can ask me later, or Olga or Mark, if our answers match given the reason for this weighting. Okay, so did this solve our problem? Let's try it again. Yeah, at least my PC works. But the deformation doesn't work, because there is no bending penalty, because we allow that the rotation differ per triangle. So we have a rotation per triangle, which means that we have some kind of rotation field in the continuous setting. And two neighboring triangles can have completely different rotations because there is no constraint on the rotation field. And this was not possible in the original ARAP, as each triangle is considered in 3 different optimal rotations of the neighboring vertices. And this overlapping inference leads to a bending penalty. The exact bending penalty is difficult to analyze, as this energy is purely discrete, but Chow and colleagues modified the original energy slightly to be able to analyze it. They suggested to not only consider spokes, but also the rim edges of the neighborhood. And this allows them to first name this spokes and rims ARAP. And I will also not derive why these edges matter so much, but they are necessary for computing the integrated Jacobian over the whole neighborhood, here, this vertex star. So instead of finding the optimal rotations just for discrete edges, spokes and rims ARAP finds the optimal rotations for the whole continuous neighborhood. And this only inserts a slight variation to the phase-wise optimization, we just need to adopt the local step by summing over the neighboring covariance matrix and average the rotations per triangle to end up in the triangle-wise rotations like before. Yeah, so the optimization is also very similar. And this allows them to find a continuous counterpart to the vertex-wise approach, which adds a bending term to the continuous energy that should be familiar to you from the last presentation. This bending term measures how much the rotation field varies by measuring the Dirichlet energy over the rotation field dr, which not dr, but r. So I will ignore the y matrix here for this presentation. You can find the details in the paper. And this solves the artifact and divergence problems at the beginning. So just by adding the rim edges, we have solved all the problems from the beginning, and this is also the reason why this is the most common used Arab energy on meshes. But it has a problem. The bending penalty is a weight, or is not a weight, but it's weighted by r squared. And this r is the radius over which we integrate to find the optimal rotations. And as we integrate over the vertex neighborhood, the vertex star, r is defined implicitly and varies over the surface. This makes the weighting mesh-dependent, which can we also see when we optimize over varying resolution. So, for example, here we see a mesh. This cuboid is deformed using different resolution, and we see that the deformation is completely different, as when we decrease the size of the triangles, the vertex star gets smaller and smaller, and therefore the R, the region over which we integrate, gets smaller as well. So we converge towards the phase Arab method because R vanishes. Which is a problem I think a lot of people ignore too often, or at least I heard that people say complaining that Arab doesn't work on high resolution meshes, which is true, but this is the reason, and we should solve this. So starting from these two papers with the phase-based energy without bending penalty and the spokes and rim energy with implicit bending penalty, other papers tackled the bending problem by adding bending penalties to the Arab energy with an explicit balancing factor that is controllable, lambda here. First, Levy and Gottsman added the Dirichlet energy of the rotation field to the energy explicitly, this time without the matrix Y. 3 years later, Chow and Grottler added a bending penalty based on the change of absolute curvature. So it measures the difference of curvature before and after the deformation, leading to a bending penalty. And last year, Öri, Herholz, and Sorkino-Hornung introduced a bending penalty based on Laplace vectors, which is also kind of curvature-based, as the Laplace vectors encode the curvature and orientation of the surface, which all have their advantages and disadvantages, but I will now present yet another energy with controllable bending. And the idea is to find a continuous, generalized, as rigid as possible energy by finding a continuous counterpart to the spokes and rim energy. And you might think, didn't I just told you that Chow and colleagues defined this energy as the continuous counterpart? And yes, but they did not derive it in the paper. They just stated it as a Taylor approximation. So we want to define our own interpretation of this continuous spokes and rims energy. First, we make clear over which we sum. So we move the minimum over which we search for the optimal rotation into the energy back again. So we can see that the spokes and rim Arab finds the optimal rotation over these two inner sums, which, and here you have to believe me, is equal to this continuous integral over the whole neighborhood of the vertex V. So the only thing left to make this energy continuous is to integrate the energy over the whole surface instead of summing over the vertices. And I skipped a lot here. The only important fact is that we have this double integral so that the optimal rotation is found over some local neighborhood. And we showed that this formulation equals the energy stated by Chow and colleagues up to fourth order. And the reason for the residual is that you can interpret the inner integral over the neighborhood as a box filter, where the neighborhood gets weighted either 1 or 0, depending on where it is. And for the derivation, we used the fact that this box filter equals the Laplace filter up to second order, to then be able to derive at the bending penalty. So we ask ourselves, if we replace the filter in the derivation, why not directly use the Laplace filter in the energy? Because it gives us the same bending penalty. And we even further generalize the energy by introducing arbitrary kernel weights, k, which are functions over the surface that differ for each point on the surface. And given this generalized energy, we can reproduce different Arab energies. First, we can choose k to be a direct delta function over v, where we only evaluate the single point, and we end up at the continuous phase Arab energy with no bending. Then we can choose k to be the box filter that I just told you, and we can end up at the continuous spokes and rims energy with the bending found by Chow et al. And if we choose the kernel to be the Laplace filter, we end up with a new energy that has the same bending as spokes and rims, but the weighting, this is the lambda, can be chosen arbitrarily, leading to a controllable bending term, which we could also achieve by defining R to be larger, so going over a larger neighborhood, but this would include an expensive geodesic distance computation, which is possible in our framework, and we tested it, but due to its simplicity, we suggest to use this as the preferred Arab energy. And it's easy to optimize this energy in the discrete setting. If you compare it to the steps of the spokes and rims optimization, the difference is minor. Yeah, we just need to adopt 2 steps when minimizing this, the rotations in the local step. First, instead of summing the covariance matrices over the neighborhood, we smooth them using the implicit Laplace kernel. Then, after extracting the rotations, we need to smooth them again using the same kernel before. Then we can have rotations per triangle that we can then use in the global step. That's all, yeah, just 2 smoothings. Notice, yeah, first, we use the implicit Euler integration for the Laplace smoothing, so we need to solve a global linear system of equations, so the previously local step is not local anymore. And second, yeah, the Laplace smoothing is over the dual graph because we smooth over triangle values, not over vertex values. This is just quick notice. Perfect. Let's look at some results. Yeah. First, we show that our bending is in fact independent of the mesh resolution. We do not suffer from the problem of spokes and rims. And the bending penalty is also controllable using lambda. When lambda is 0, we end up with the same energy as phase Arab, and when lambda goes to infinity, we only allow for a single global rotation for the whole mesh, and the rest is done by stretching. We also compared our results with the methods that I presented earlier, that also have bending penalties, and all are capable of producing reasonable outputs. I will not judge them. Yeah. I will judge them later, maybe. Compared to spokes and rims Arab, our method takes around 50% more time for the pre-computation, as we need to factorize 2 Laplacian matrices, and in each iteration, we also need to solve 2 more linear system of equations. This might seem very expensive, but if we take a look at the convergence speed against wall clock time, we see that our method is very fast. Yeah? So lower and steeper is better in this graph. And you might not be able to see this, but all methods that include an extra explicit bending term outperform spokes and rims, and our method is the fastest. At least in this example. I know, yeah, this is cherry-picked, but in general, we saw that the method by Ori and Al and our method are usually the fastest. And yeah, I have to say that in some settings, we lose our speed advantage. Yeah, I can tell you about that later. But we have other advantages over the other methods. First, the method by Levy and Gottsman can sometimes converge really, really slow. This example, for example, took over 7 minutes, while our method only took 2.6 seconds. And this is actually something that was stated by the authors, and they suggested to use a multigrid solver, which we could also use, so we didn't compare this. Yeah. Second, the method by Zhao and Grotler has the problem that it measures absolute curvature. So absolute curvature cannot distinguish between convex and concave regions, so sometimes the mesh flips because it is not penalized, leading to these unwanted artifacts. And anecdotally, I can tell you that this method is the least stable one out of all these methods. And lastly, the method of Ori et al. Does not converge sometimes. Yeah? Here, for example, the eye of the auger will continue to circle around, and we ran this, and we saw, if you take a look at the top, the energy gets into a loop over and over again. But I have to be honest, our method is also not perfect. If you have constraints that are difficult to achieve using just rigid deformations, our method tends to produce spiky results, like the spokes and rims Arab. And this is actually the main reason or the main motivation by the method by Ori and colleagues. So it is no surprise that their method leads to much better results in these scenarios. Okay, so in summary, we presented a generalized as rigid as possible energy and adopted the spokes and rims optimization framework for a special case of this energy that gives us more control over the bending energy while keeping its simplicity. And what is the takeaway message? Whenever you use classic Arab or you want to use as classic Arab, try this, please. Yeah, because I think this is, it captures the core idea of the original as rigid as possible energy, and it makes everything controllable. So, although I hesitated to say this out loud, but right now I think this method is Arab done right. So, thank you.
Thank you very much. Other questions for Hugo? Yes, I see one question in the back of the room. Olga.
Thanks for the nice talk. Amazing how much one can milk of a very simple idea that I could implement in 2 days 20 years ago. I have a question and a comment. So the reason why we took the sum of the Khotan weights was very simple. I was working on meshes that were just quad grids divided diagonally into triangles. And I was noticing that without this weight, or the weight being 1, I would just get very asymmetric results. And if you have the Khotan alpha plus Khotan beta, then the diagonal cancels out. So you didn't explicitly talk about the symmetry, you talked about the scale issue and you solve it, but can you say, like, is it indeed also solving the asymmetry issue?
No,
Thank you.
Unfortunately not. Yeah, this is actually a thing that I want to further look into. It does not solve the symmetry issue. There was a paper 3 years ago where I solved the asymmetry issue
with intrinsic
using intrinsic triangulations, and I thought I could use this same idea to just integrate over the Voronoi cells. Using the same approach, but this doesn't lead to the expected results. We still get asymmetric results, which is, yeah, a bit of a bummer, but I try to use the intrinsic Delaunay triangulation to solve this problem using this energy as well right now, or at least a student tries to solve this problem. But,
student,
yeah.
Oh. Cool, thank you so much.
One more question. Yes. In the front of the room, please.
So very nice talk, thank you. So in this context, this Laplacian smoothing of the Jacobians can be interpreted as a bending regularization. But I could imagine, even if you were doing planar deformation, you could still do this procedure and it would change something, right? Or let's say we had like a tet mesh in 3D, we could do the same thing, but tet meshes in 3D can't bend, so to speak. So how would you interpret what you're doing in that context?
I actually don't know, because I thought about this, because the Chow et al. Paper was actually about tet meshes or surfaces, not surfaces, but tet meshes or just in the 2D Euclidean plane. And there everything works, because just if you don't have a bending term, just the stretching term, you still have a bending penalty, because in ambient space it is kind of measuring something. But we added this rotation, or this regularization on the rotation field. So I thought about this: if you have a tetraregularization and you kind of rotate it without stretching, so maybe you twist it this way, yeah? Then you have something that is not measurable using the original formulation, but now we can measure this. So now it gets penalized using our rotation smoothing. So I don't know if this answers your question, but I think it goes in this direction. So I still don't know what it really measures in Euclidean space, but I think it's worth testing it.
Thank you.
Okay, I see that there are no more questions. So, one quick question.
Thank you for the very nice presentation. I was wondering, since now lambda is a free parameter, have you like maybe you speak about it in the paper, but like kind of an automatic choice, like if you do some sort of dimensional analysis to pick lambda in a way that makes the physical units of the deformation coherent?
So we found that this lambda relates to r squared, and r squared is the radius, so it is some area dimensional term, and there's also a constant ratio between them, so you can kind of exchange them, the lambda and the r, or the intended influence in the neighborhood. So yeah, you can measure it.
Okay, great, thank you.
But give it a meaning.
Let's thank Hugo one more time.